Okay, section 7.2, find the domain of the function. And for the most part, when we're asked to find the domain is just the values that x can be. So for the most part, what we're trying to avoid is any values of x that would make the expression undefined. If you remember, anytime we have a 0 on bottom, this expression 5 over 0 is undefined. That's not something that we can give a numerical value to. So we'll come back to this function f of x in just a second. But if we had something like, let's say 5 over x, we'd say x can be anything but x cannot equal 0. Because if we have 5 over 0, we have an undefined function. So we got to make sure that our denominator does not equal 0. In this case, when it's just x on bottom, that's easy enough to figure out what x cannot be. So if we go back up, we've got this function f of x equals 8 over x plus 7. So we've got a similar deal. This, let's use green. This denominator cannot be equal to 0. So you might ask, what value, if we put it in for x, would make that denominator 0? Sometimes people think that 0 would be it, but if we put in 0 for x, we get 0 plus 7, which would make that denominator 7, which is fine. So 0 is not going to be a restriction in this case, but x cannot be negative 7. If you think about x plus 7, if x is negative 7, we've got negative 7 plus 7, which would give us a 0. So this is the one thing x cannot be. So if we're writing that in terms of the domain, we're saying, again, x can be anything, but x cannot be this 7 here. X cannot be negative 7, rather. So the way that we write that is we use this set notation, x such that x is not equal to negative 7. So x can be anything as long as it's not negative 7. So that's going to be our answer in that case. And next up, we've got a question asking us to do the same thing. Find the domain of the function p of x equals 2x minus 2. So we're basically doing the same thing. We're finding out the domain, which is all the values of x. Let's use a different color. The values x can be. And like I said on the last problem, typically what we're trying to avoid is an undefined function. And in this case, since we don't have any variables in the denominator, we're not going to have any undefined possibilities. So if there are no variables in the denominator, then x can be anything. Okay, so in other words, we don't have any restrictions, and then x, we can write this as x such that x is a real number. Okay, so not anything that x cannot be. And again, just want to go up and emphasize this. Since we don't have any denominators with an x in it, here we've just got our function is 2x minus 2. No denominators there other than 1, so not going to have any restricted values there, nothing that x cannot be. And in this third example, p of x equals x squared plus 9. Again, we're mainly looking to prevent any sort of undefined fractions to figure out the things that x cannot be. In this case, x could be 0. 0 squared plus 9 is just 9, so that'd be fine. X can be negative numbers. If we had negative, let's say 3 squared, that's okay. We can have that. That's not undefined. Basically, we don't have, let me erase this just a bit. We don't have any variables in the denominator, so we're not going to have any restrictions. So just like the last problem we looked at, x can be anything. So x, the set of all x such that x is a real number. Okay, so that's how that solution is going to go. And in our fourth example, g of x equals 1 over 10 minus 9x. So in this case, looking for the domain, the things that x can be, we've got a variable in the denominator. So in this case, we can't say that x is any value that's a real number because there's at least going to be one thing that x cannot be. So what we want to avoid is this denominator equaling to 0. So we might write it, let's see, move that off to the side a bit, say that 10 minus 9x. We're not concerned about the numerator because the numerator can be anything. But this denominator here cannot be equal to 0. So we're just going to do a little bit of algebra in order to figure out what that x is. This works just like an equation, even though we're saying not equal to. That's what that equal sign with the line through it means. So ultimately, in order to get the x by itself, we want to get rid of that negative 9. We want to get rid of that 10. But we've got to get rid of that 10 first, so we're going to subtract 10 from both sides. And now we've got negative 9x is not equal to negative 10. Trying to get x by itself, divide by negative 9. And those cancel out. We've got x is not equal to negative 10 over negative 9. Anytime you've got a negative over negative, that just becomes positive. So x cannot be 10 over 9. So when we're writing our domain, x, and we use the set notation, x, it's all values such that x is not equal to 10 over 9. But other than that, it can be anything. So our domain is going to look like that. And our last example, find the domain of the function f of x equals 9 over x plus 5. Mainly doing the same thing that we've done before. Looking for the domain, and again, that's the values that x can be. So we're trying to avoid anything that's going to make an undefined fraction. So this denominator here, x plus 5, cannot be equal to 0. And this might be one that you can just do in your head. X plus 5 cannot be equal to 0. We want to subtract 5 from both sides. Bring down your not equal to sign. So we've got x on the left, and then 0 minus 5, negative 5. X cannot be negative 5. And we're writing that in set notation. Your domain is the set of all x such that x is not equal to negative 5. So not too bad. That's all there is to 7.2. Good luck.